My, such energetic faces. All of you were so post-HB ready, with dinner being the last thing on your mind. Anyway, so with that, today I'm going to be talking about post-HB stars, and in particular, the search for post-HB stars in Magellanic Clouds. I'm going to be talking to you about the need for the survey itself, and the outcomes. So, before I get into So before I get into the survey, I'd just like to set the scene, because we've been talking about PLANETs the whole day. So the post-HB phase is the intermediate phase between the AGB and the PLANETary nebulae. For single stars, the evolution is pretty simple. A super-wind mass loss rate of about 10 ⁻⁴ solar masses per year terminates the AGB, and the star moves on to the post-HB phase, where it evolves with a constant luminosity and increasing temperature. At about 30,000 Kelvin, the star begins to ionize, the outer shell begins to ionize, and the star moves on to the PLANETary nebula phase, and eventually follows the white dwarf cooling track. So just to give you a feel for what post-HB stars are like, they're mostly A to F spectral types, AFGK. Their masses on post-HB is about 0.6 to 0.8 solar masses. They have a lot of morphological changes that happens from the AGB till the end. For instance, the radius of the star, the central star, changes from about 1 AU on the AGB to about the white dwarf radius, which is approximately the Earth's radius. Post-AGB stars are variable. On the ATAR diagram, they cross the Cepheid population to Cepheid instability strip, and observationally they can be they can range from being obscure to completely naked. So you kind of, there are some stars you don't really see at all in the optical because you can't basically observe them. So that sounds really simple now, doesn't it? But what we really see when we observe post-HB stars is that they're really, really diverse set of objects. So what this tells us is that we have no good statistical picture of post-HB evolution. And it's not just single evolution that is the evolutionary channel for these objects. There should be more than one evolutionary channel for these objects. So it's important to study the post-HB phase to understand the late stages of stellar evolution and stellar evolution in general. So studies started with the galactic post-HB stars because they're in the galaxy, they're close. It started in the mid-80s. The Tolan catalog by Riviera catalogs about 400 galactic post-HB stars. They're quite well studied. For instance, from the SEDs we find two distinct populations. What I show here is the SED of one of the populations, and as you can see, there's a double-peaked SED. This indicates that there's a expanding, so the central star peaks in the optical, and this peak in the infrared is basically the peak from the expanding shell, cool, dusty shell. So we expect that this kind of SED is shown by single stars because the super-wind mass loss kind of rejects the envelope, and then you see the star, and then you see the envelope around it. Then we have another set of objects that have SEDs which have a broad excess with an onset in the near-infrared, which indicates that there's hot dust in the system in the form of a stable, rather stable capillary disk with orbital periods. From observations, we find that the orbital periods are about 100 to 2,000 days. So we find these two distinct populations basically. So we also see from the SED that they're pretty multi-wavelength objects, and one of the main characteristics being they have a very large mid-infrared dust emission. So a mid-IR excess is a very good way to identify post-HB stars. Now we have them in the galaxy, but the problem is that like Riviera mentioned, the distances to the galaxy is unknown, so we don't have luminosities and initial masses. So we decided to search for them in the Magellanic Clouds because we know accurate distances to them, which means luminosities and initial masses. And that's where I and the survey come in. So optically visible post-HB stars in the clouds. The SEC paper has been accepted. It's going to be out in MNRAS. The LMC paper is on the way. It will be dished out very soon. So what we do is we look for candidates with a mid-infrared excess, and we select these from the mid-IR Spitzer Space Telescope surveys. And the work as such is basically involves candidate selection, a detailed spectroscopic examination, SED CD analysis, variability analysis, and finally what you get is a spectroscopically verified catalogs of post-AGB, RGBs, I'll get to that, and other interesting objects. Now before I move on, just to remind you again, the photometry we use covers the optical, the UV, optical, infrared, and mid-infrared bands. Okay, so we start with the selection criteria. So the selection criteria is twofold for both the LMC and the SMC. One is the color criteria, which makes sure that we have objects that have a 8 micron or a 24 micron detection, which means that there's a percent of mid-infrared excess in these stars. And they have to be optically visible, of course, because we're trying to get optical spectra to observe them. And I won't go into the detailed candidate selection because it's probably going to keep you away from dinner, and I don't want to do that. So I'm just going to say that we use a rather robust selection criteria, and we kept slightly relaxed because sometimes more is more. And we get about 1,200 objects in the SMC. Now, you see here a luminosity criteria. The reason is because a luminosity criteria helps reject contaminants such as supergiants, which are also pretty dusty, but they're luminous, so we can reject them, and low-mass YSOs, they're low-mass, low-luminous YSOs, so this number here, luminosity less than 500, rejects these objects. Now, in the LMC, we selected about 9,000 objects. Now, this was done by Else van Arl. She did a photometric study or search for post-AGB candidates, so we used her sampling set. So now we have our selection, our objects defined, and the next step is to go and get spectra for these. And we did that by using the AA omega multi-fiber spectrograph. It covers the 2-degree field, 400 fibers. You get 300 sine star gets out when you remove all the sky and all the other blah. And it was on the 3.9 meter telescope at the AAT. So we basically get low resolution optical spectra of about 1,300 resolution, going from about 3,700 angstroms to 8,700. So it's an entire optical spectrum, mostly entire optical spectrum. Now what I show here is the fields we observed. So the SMC is nicely covered, and we have a total of about 800 spectra. And that's the LMC, which is also really nicely covered. We get a total of about 2,000 spectra. So from the selection criteria, like I said, it was rather relaxed. So there's other objects that have mid-infrared excesses. But these objects can be weeded out when you look at their spectrum. So what we have to go and do is we have to go into a visual, preliminary visual spectral analysis to weed out contaminants like C stars, M stars, quasi-stellar objects, redshifted galaxies, PNs, and YSOs. So we have catalogs of these objects as well. Some of them have been observed and some of them are new. So when you're interested in any one of these, you can always take them. And then we're left with this bin called possible post-AGB and YSO candidates. Now why are the YSOs here? Sneaky little things. Now the reason is because the massive YSOs do not get cut in the luminosity cut because they're still there. They have similar SEDs and they have spectral types ranging from AF, GK again. So you really can't, I mean there's no way to really take them out looking at their SEDs or spectra. But there's one way. The way is the log G, the surface gravity, differs by a factor of 1.3. So if you can determine stellar parameters from the spectra, which is what we intend to do, you can separate the YSOs and the post-AGB stars. So we take this bin, so we're left with possible 150 candidates and 500 in the LMC. I must mention that the LMC is rather halfway, so the numbers could change a little bit in the paper, so in case you plan to read the paper. So what we did, we took the bin and we put it into a fully oops. Okay, that's pixel heavy, that one. So we put it into a fully automated spectral typing pipeline. Now what the pipeline does is it takes the spectra, observed spectra, it matches it with synthetic templates, and then it simultaneously fits for TEF, temperature, log G, and FUNH, and that's what you get over here. So based on the log G, like I said before, we were able to separate between post-AGB candidates and YSO candidates. So we found about 100 post-AGB candidates in the SMC. And this is the first catalog of post-AGB stars in the SMC and the LMC. And remember, they have luminosities and initial masses, so they're extremely useful if we really want to study the evolved stages of stellar evolution. And in the LMC, there's about 350 of them. I just have to make a disclaimer that there's observational biases because we only look at the optically visible ones and A to K spectral types, of course. But derive luminosities and EB minus V, and also just generally look at the SEDs. Now we found that just like in the galaxy, the LMC and the SMC also have two similar populations called of the shells and the disks. And we haven't had radial velocity monitoring for the LMC and SMC sources, but we think that they will also have Y orbits, which is why they have the onset that happens at the near infrared, which means there's hot dust in the system, which means that it has to be Y binary systems that we see here. And that's what so the disk sources are likely to be Y binaries, and we think that these Y binary post-AGB systems probably evolve into axisymmetric PNE that we've been talking about all day. Before I move on, I'd just like to say that so the shells and there's disks. Just remember that. So now what we did is we plotted all the candidates. This is the Y-source. You can ignore this for now. The reason why I have it here is because the log G's vary by a factor of 1.3, and the error bars from our spectral typing pipeline is about 0.5 in log G. So it's possible that some of the Y-sources are post-AGBs, or some of the post-AGBs are Y-sources, but most of them that we've monitored with high-resolution spectra from UVS and the VLT seem to be right in the right place, so we're happy that our code's pretty robust. So we put the stars in the HR diagram, and we find that a lot of the disk sources, the open symbols, I'm not sure if you can see the symbols, but they're open ones, which mean the disk sources, the binaries, and the likely binaries, very likely binaries, and the closed ones, which are the shell sources, and the crosses, which are uncertain. So there's very few shell sources strewn across the HR diagram. A lot of them are disks, and a lot of the disk sources evolve off the RGB, which means that a lot of the post-RGB stars are actually disk sources and therefore binaries, because you wouldn't expect single stars to evolve off right off the HB. Now what this tells us is that if you find this in the LMC and the SMC, it's very likely that a lot of the galactic post-RGB binary stars that you're looking at are also, post-AGB stars you're looking at are also post-RGBs, and you just can't tell because we don't know luminosities to them. So that's one of the other interesting outcomes that we find. Right, so that's the end. I'm so nice, I'm going to let you go. So the takeaway message is basically that we have spectroscopically verified catalogs of LMC and SMC, optically visible post-AGB and RGB stars. These sources are very common in the post-AGB and post-RGB phase. And they are likely connected to binary evolution channels, which avoid spiraling, which means that they have about 100 to 200 day periods. And these objects, we think, should evolve into axisymmetric PN. And finally, post-RGBs, I'm sure that they exist in WISH or that they exist in the galaxy. And just because we don't know luminosities, we still call them post-AGB stars. I'll take questions now. Thank you.
First, I commend you on the very nice work of dealing with that large sample. But I guess I have a question here. Well, why do you think that the disk sources will evolve into PN? The disk sources in our own galaxy, we really don't see nebulae around them by and large. And so I wonder that these would evolve into real PN.
So the PNE that we see, like the ones Ursula observed, they're binaries. They're probably, but they're ones with compact periods, right? So these ones that have long periods, I think that they will evolve into PNE, but it's just that we don't observe them because it's just really hard to observe PN with central stars having really wide systems. I mean, why wouldn't they not evolve into PNE? Because what we expect is that they will evolve into having asymmetric nebulae.
I think what Bruce is saying is that observationally.
Yeah, observationally it's really hard because how are you going to monitor central stars with? I mean, it's possible if you really look for it, you'll find them, but I think.
Well, we should be seeing the ejecta.
Yeah.
In PLanetary nebulae.
Yeah.
Which are simply posted in the stars in the center.
Yeah.
You see the ejecta.
Yeah.
But in the galactic.
Yeah.
Resources which are this prominent, you don't see the extent of why.
Well,
We do see them.
We do see them.
We do see them.
But the only difference is that we see them with compact systems.
Sorry?
In the red rectangle in 89 Hz, those outflows are very puny. Right?
They are
So the
there.
question is, so what Bruce is saying there is, do you think that really red rectangle and 89 Hz will evolve into asymmetric PM?
I think so. Yes.
Yes,
Yes,
that's
I
what
think
we
so.
expect them
With the
to.
large number that Hans has looked at, these seem to be more the exceptions in terms of seeing the nebula.
If I can interrupt, I think these are probably fairly strongly connected to the long periods. We don't know the periods very well, but we can see that there's a long period binding there because we're finding chemically polluted secondaries. We're seeing secondaries, main sequence secondary stars with carbon abundances or barium abundances that shouldn't be there. So there is definitely a population of PM that correspond to this, and morphologically they also all show very, very strong equatorial enhancements and very, very faint lobes. So I think there's a connection there.
Joe?
Just to add to your story, in the other mass direction, there's a class of supergiant B star, B bracket E supergiants,
Yes.
which actually Bruce and so I've worked on, and their spectral energy distributions are a dead ringer for what you have here.
Yeah.
So it seems that it's really interesting that you found the post-red giant range population. It seems like this is a phenomenon that extends all the way up and down the evolved star sequence.
Well, I mean, all you need is a material close to the star, which is hot enough. So which is a disk in the PE things which you're
The
talking about.
interesting thing is, it seems that something has stunted the growth of, stunted the evolution of these sorts of objects, perhaps. Or I think it's an open question as to whether they're going to become planetary nebulae or not.
But this has been discussed in the past in conference that things like the red rectangle are probably just not evolving at all because there's infall back onto the star, which is preventing its evolution towards the planet nebula. I mean, Sunquark calls this a stationary object, it's just not evolving.
We estimated evolutionary rates for both the phases, and we find that they last longer than post-AGBs because of the infall. So they have longer rates than post-AGB evolutionary timescales.
Yeah, much longer. For example, if you believe the few objects, very large, extended pre-planetary nebula, the frosty Leo nebula, even the red rectangle, if you compute its extraction age out to the outermost edges where the rectangle is seen, it's 6,000, 7,000, 8,000 years, which is way too long for an object to be spending in space. So obviously the relation has been detected. Yeah, so yeah.
From the ratio of these kind of objects to those planetary nebulas that are in the clouds, you can probably find they come out to have about the same time scale, the same lifetime, essentially. I mean,
yes, it's yeah. I mean, are you talking about evolutionary rates or numbers?
no, I'm talking about numbers, just numbers, hard numbers. How many planetary nebulae in the SMC? How many in the LMC?
Yes.
That's comparable.
Well, okay, so let me explain. So what this plot here shows is that it shows post-AGB, post-AGB evolutionary tracks from Schoenberger, and so we did this back of the envelope calculation, and we find that we should expect about 100 stars in the LMC and about 15 in the SMC. But this is taking into consideration that they're all single evolutions, so they go really fast. Which means that if you had reaccretion, the numbers would go much higher. And since our sample has mostly disk sources, and which is reaccretion, we can expect that this number is much larger than what we observe. But still, we're slightly off, because if we expect about 100 in the LMC, and what we see is about 500 or 400, then it's a bit, yeah. But yeah, we just have to remember that there's no reaccretion taken into account in these tracks, which is why your numbers are slightly low.
No, what I'm saying is that the number of PM in the clouds is similar, astronomically speaking, to the number of objects that you're finding, which would tend to make me think that they have the same duration in those phases.
But if you don't see and
because they would come, because they would be coming from the same type of object. difference in
Sure. Yeah, you expect them to be the same.
Let's carry on more detailed discussions tomorrow in the discussion section. I think everybody is wanting to go out for dinner now, so.
Well, thank you for your attention. And
Thanks very much.
Christoph.